Alrighty, my people, how are we? Video 3 for u-substitution. Gave you some sort of more normal examples in the first video. Last video we did ones that were thematically kind of linked because they were either arctan or had a denominator that looked like arctan. We're going to go ahead and just do kind of a variety on this one. We're going to go ahead and start off with this one. Now this one should be, and we'll bounce back and forth between the easier ones and the more difficult ones. This one ought to be pretty straightforward. Cosine over here is not going to be my u because there's something more complicated right here. This even looks like a composite function, right? This looks like my f prime of g of x, okay? So if this is the inside, then it's probably a good idea to go ahead and identify u as sine x. Now we're going to go ahead and get our du, and we can go ahead and determine whether we have chosen a good u value by when we get our du, we'll be able to determine whether all the pieces are there, right? And so du is going to be cosine x dx. I have a cosine x, I have a dx, woohoo! Okay, so what I have then is sine of u du. Now remember, this is a definite integral. It has limits of integration, and therefore it's going to require that I change the variable or change the limits of integration from being in terms of x to being in terms of u. Okay. Now if I plug in 0 for x, sine of 0 is 0. Pi over 2. Sine of pi over 2, when x is pi over 2, sine x is going to be 1. Okay. So basically I need to integrate sine u du. We've already seen that in one of the previous videos. It's negative cosine u from 0 to 1. And you can leave the negative outside if you want. It doesn't really matter. Cosine of 1 minus cosine of 0. Of course, that negative could just flip this difference around. And we know cosine of 0 is 1. So 1 minus cosine of 1. And we would need a decimal approximation for that. Make sure you're in radians. 1 minus cosine of 1. And that gives us 0.460, okay, as the area under the curve. Now let's go ahead and actually check this by using our calculator, okay? Let's go ahead and do alpha f2, get an integral up there. I have 0 to pi divided by 2 of cosine x, close parens, sine of x, and is that enough parentheses? No, it's not. And we'll do that in terms of x, and go. And it is exactly what we got above, okay? 0.459697, blah, 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 which basically, when you round it, becomes 0.46, okay? Let's go ahead and move on to our next problem. This one is going to be, I hope it shouldn't be too difficult for us. Sine of natural log of x over x dx. Okay, well, I see something stuffed inside of something else. I see a natural log stuffed inside of a trig function. I don't usually see that, so that just screams composite function, right? So let's go ahead and try out a u expression of identifying u as natural log of x. Now, if I do that, then my du is going to be 1 over x dx, which I hope you see, because you can remember, basically take that numerator out as sine of natural log x, and you can leave, instead of dividing by x, multiply that numerator by 1 over x. This right here is my du, and this right here is my sine u. Oh, so many of these wind up being sine u du, but sine u du it is, and we get negative cosine u plus c, which is negative cosine of natural log of x plus c, and that is our indefinite integral. Alrighty, let's go ahead and this one will be hopefully kind of fun. How about, wrong pen, e to the x over e to the x plus 1 dx. Okay, well, it is in a rational structure. Now, if it was, something like e to the x plus 1 over e to the x dx, when we asked ourselves, can I change the form and get rid of the rational structure, the answer would be yes. You would separate the fractions and you would get something like 1 plus e to the negative x dx, and it wouldn't be a substitution problem, it would just be changing the form, right? But we have the reciprocal of that over here, so that's not what we're going to be doing. We're going to be doing something different. We're not able to get rid of its rational structure like we did over here. We need to ask ourselves the next question, which is the numerator the derivative of the denominator? And in fact, it is. So since we suspect that it's going to be natural log, we're going to take that whole denominator and make it u. Du becomes e to the x dx. I have everything that I need. I don't have to multiply by anything in order to actually have du. Du is given to me by these two factors right there. And I have du over u, or I know some of you prefer it like this, doesn't really matter. And the answer is natural log of u plus c, or the natural log of e to the x plus 1 plus c. And again, I will remind you that when you're dealing with natural log, you need to remember that there is a possibility of needing those absolute value bars. Of course, e to the x is an exponential. Exponentials can never be 0. They can never be negative. And therefore they are always positive, and always positive plus 1 is still always positive, and therefore it does not, since it doesn't have the possibility of being negative, it doesn't need the absolute value bars, and so we just leave them out. Okay? What if, though, we had 1 over e to the x plus 1? Because that is a possibility. And this actually is integrable. We can do this. The question is, how? Well, let's go ahead and just think through our questions. It's an irrational structure, so we ask ourselves, can I get rid of the rational structure by simplifying? And the answer is no. Is the numerator the derivative of the denominator? And that's no again. Is it arctan, or is it an inverse trig function? Now, it could be if it were something like e to the 2x plus 1 over e to the x dx, right? Because that would be arctan, because the numerator would be the derivative of the thing being squared. I would use my rules of exponents to transform e to the 2x to e to the x squared, and that allows me to identify the arctan. Okay, that would actually be, that would basically be arctan of e to the x plus c, and that would be your integral. This one, however, takes a little bit of, let's say, love in order to get it to where we need to be. Now, if you're thinking to yourself, well, golly, I really wish that this was the same form as that. And by this time, you should know that any time I say, gosh, I wish, we're going to do it. right? I'm going to change this such that this is a possibility, okay? And here's how I'm going to do it. And this is going to frustrate some of y'all, and but I've done stuff like this before. If I add e to the x and then subtract e to the x in that numerator, I have not changed the value of that integrand, right? Because I've added a quantity and then I've subtracted it again. Now that I have it like this, I can now separate the fractions. Minus e to the x over e to the x plus 1 dx. And this, of course, simplifies to 1, and I'm going to get 1 minus e to the x over e to the x plus 1 dx. Well, I already know how e to the x over e to the x plus 1 integrates. That was my previous problem, right? And I know how 1 integrates. It goes from 1 just to being x. And so what I have is that. X minus natural log quantity e to the x plus 1 plus c. Okay, and that's one of those change of forms that doesn't come to people's minds all that often, right? It seems to me that we're more okay with sort of unsimplifying fractions, right, than we are with adding and subtracting random expressions or values. And I think that's because we're used to unsimplifying fractions when we get a common denominator in order to push them together. This sort of simplification or unsimplification just doesn't pop up as often, so we're not used to seeing it. But we should, and what I'm trying to impress upon you is the fact that every once in a while, when we say to ourselves, gosh, wouldn't it be nice, we need to remember that we can make those things the case more often than you might think. Okay? I have the integral of x squared over the square root of 1 minus x dx. Now, you might be looking at it and going, there's no way that this is possible. Okay? It is possible. We did problems like this on Tuesday when we chatted about this, and one of those problems, or more than one of those problems, is on there. The problem is the fact that you're going to sit there and you're going to let the x squared distract you, because you know in your heart of hearts that u needs to be the radicand. And you know that that means that du is negative dx, right? Because the derivative of 1 minus x is negative 1. What you're not taking into account is the fact that if u is equal to 1 minus x, then x is equal to 1 minus u as well. And I can use this for the radicand, I can use this for the numerator, and all I have to do is I have to go ahead and put a negative in there and a negative out in front to basically accommodate for my du. And so let's go ahead. We get negative. This down here, it's a radical in the denominator, so it's that quantity to the negative 1/2. So that's u to the negative 1/2. X squared, and x is 1 minus u. Remember that 1 minus u and u minus 1 are the same thing when they're raised to a even power. So I'm just going to call it u minus 1 squared. And then my negative dx becomes my du. Now, this is still a little bit complicated, but you should be able to see that this is quickly becoming more manageable. And we can basically now take this u to the negative 1/2 and distribute it and by means of our rules of exponents, we basically get power rule terms in our integrand. And basically we need to integrate u to the 3/2. That becomes u to the 5/2 over 5/2, or let's call it 2/5. I'll leave this negative out here and I'll distribute it here in just a second. This becomes -2. The u right here becomes u to the 3/2 over 3/2, or times 2/3. This becomes u to the 1/2 over 1/2, right? And then plus c. Sorry, I didn't leave myself a whole lot of room. We'll just sort of tuck that plus c in there. Now remember, when I distribute the negative, that's not going to impact the c, because negative c is also just some constant, okay? Let's go ahead and clean it up. That becomes 2/5 u to the 5/2 plus 4/3, or I'm going to distribute the negative, -2/5 u to the 5/2 plus 4/3 u to the 3/2 minus 2 u to the 1/2 plus c. And then I need to go ahead and take my u and substitute back in, so it is now back in terms of the original. And that ugly thing is the solution to my integral. Okay? And all of it hinged upon just that one extra step of, gosh, that x squared is annoying. That doesn't usually happen. That isn't usually there. But if we take this and take u is equal to 1 minus x, subtract u from both sides, add x to both sides, and we get x is equal to 1 minus u, and that is what goes in here. Once we get this down here in terms of a monomial to a fractional exponent, then once I've FOILed out that binomial squared, I can then distribute it across, and I just go term by term in terms of undoing the differentiation of by power rule. Now, that is it for video 3. I got a couple more problems, so we'll do video 4, and at that point you will have gobs and gobs and gobs of problems to help you make sense out of u-substitution. I hope this has been helpful. If you have any questions on one of these problems, please do let me know either on Tuesday or by a message. See ya.